Good morning. My name is Ben Bussey. I'm the Group Supervisor of the Planetary Exploration Group at Johns Hopkins Applied Physics Lab. And I'm going to talk to you today about what we know and a little bit of history about the illumination conditions at the lunar poles and how that's enabling, I believe, the surface operations and some of the tools that we've developed. Now, a lot of the research that I'm going to show you, I've been looking at the illumination conditions now for a scary number of years. But most recently, I've been supported by two NASA funding mechanisms. One is the Lunar Science Institute. I'm PI of one of the polar team. It's just coming to an end now. And the theme of our team was exploring lunar incognita. When we started this project in 2009, the lunar poles were relatively unexplored, unknown. Remember, this is pre-Lunar Reconnaissance Orbiter and pre some of the other international missions. So our team consisted of 9 interlinked research tasks, looking at everything from redoing polar geology, you'll see here illumination and thermal studies, volatile modeling, so predicting if a comet hits the moon, how exactly do these particles move around on the surface, and also how do they interact at the grain level, so what mechanisms might keep them to be stored. And towards the bottom here, you see surface science, instrumentation, and operation. And we were looking at some of the engineering sides too. So here, surface mobility and excavation. We had a team led by Jerry Johnson in University of Alaska. The bottom 2 pictures show a model that he's developed that predicts the forces associated with a rover wheel. And the 2 pictures on the above actually show a rover wheel being used in a lab. So we would measure the forces and then compare that with the forces that the model predicts so that we could then validate the model. And having done that, we could use the model to run for conditions that you can't run in a lab, like the 40 Kelvin temperatures I'll be talking about. Most recently, we were fortunate enough to be selected as one of the new SOVI's Solar System Exploration Research Virtual Institute, and we're one of 9 teams where we will continue our work looking at the moon as well now, asteroids and Phobos and Deimos. And a large part of this work will also include continuing to understand the illumination conditions, which are intrinsically linked to the thermal conditions and hence the storage of volatiles and how you might extract them. So why are the poles important? The lunar poles are potentially unique in the solar system in that whereas the Earth's spin axis is tilted at 23 degrees, which is why we get our seasons, the moon is only tilted at about 1.5 degrees. And this causes what I put here as unusual illumination conditions. First of all, we can get areas of quasi-permanent sunlight. So if you're on a mountain close to one of the poles, it was predicted a long time ago that you might see the sun a lot of the time. Remember, at the equator of the moon, you get 1 lunar day, which is 28 Earth days. You get 14 days of sunlight, followed by 14 days of darkness. So 2 big advantages if you've got places that receive far more sunlight than that. One is you've got obviously a lot of solar power. You've got an ability to generate electricity using solar power. The other is a relatively benign thermal environment. Again, a place at the equator on the moon goes from about plus 120 Celsius at local noon to minus 150 Celsius at midnight. So whereas a place which is got sort of a constant grazing solar instant angle, remember if you stood at the pole, the sun would be on the horizon and it would sort of track along the horizon every 28 days. And this would be much more constant temperature of about 220 Kelvin, about minus 50 Celsius. Also, places which are sort of depressions, or and the moon is like covered in impact craters, so you've got lots of holes in the ground. These places have a good chance of being permanently shadowed. And as such, initially it was modeled that they would be 50 to 70 Kelvin. Now, thanks to the Diviner thermal instrument on NASA's Lunar Reconnaissance Orbiter, we now know their actual temperatures, and in fact, temperatures actually get down to less than 30 Kelvin. And these serve as cold traps for volatiles. The poles are also good from an exploration perspective because you do at least get roughly 2 weeks of Earth visibility every lunar day. So, to start you off with a little bit of history, before the recent armada of foreign missions, the best information we had came from the Clementine mission, which was early 90s, a joint NASA-DoD mission. And it was the first mission actually to fly a digital camera to the moon, and it gave us our first good look at the poles. I mean, the moon was well studied in the 60s by Lunar Observer in support of the landing, but they concentrated on the equatorial regions because that's where the people were going to go. So this shows a collection of images that the small crater here on the right of the two that you can make out is Shackleton crater, about 20 kilometers across. And this movie covered one lunar day. So what did we learn? Now, Clementine mapped the moon for 71 Earth days, for just over two lunar days, and it arrived just in midwinter. Now, remember, you think about Antarctica in midwinter, it's totally dark for months at a time. And similarly, the moon should be similar, except the lunar Antarctic circle should be at about the 88.5 degrees. What we found is, I'll put these upside down, the top is actually the South Pole, is we did find that a lot of places are actually lit even in the middle of winter. We did find, though, that nowhere got constant illumination, but several places marked here as ABC were lit for more than 70% of the day in winter. The North Pole, the data were collected in roughly midsummer, and we did this large crater here is Peary crater, named after the American explorer, and that's about a 78-kilometer diameter crater. And we did find 4 places on the rim of Peary that were constantly illuminated during a lunar summer day. But we couldn't claim that they were permanently illuminated because, again, the data was collected in summer. The next thing we tried is, the title of the presentation is to do with simulations. The reason we want to do simulations is an image is obviously a very good tool for showing you the exact illumination conditions at that instant in time. But it has a couple of limitations that you can overcome with simulations. The first is you can run a simulation at any chosen time that you want. So if you're running a mission, you want to know exactly what your lighting is going to be like. You can't necessarily get that unless you have an image with the same solar conditions. Also, if you want to investigate the effect of using a mask, simulations help. So the top two here show simulations we did corresponding to the same lighting conditions as the Clementine images shown below. And you can see the simulations do not match very well. Well, the left-hand side, left-hand one matches fairly well. There's a bit of noise in the data, but the right-hand one doesn't match the actual image at all. And this is because the topography at that time wasn't of a high enough fidelity to allow one to do this. So in order to start doing simulations, we actually did some work using realistic craters. So this just shows an image where we looked at simple craters less than 20 kilometers in diameter. And we could use this to start to learn about how much permanent shadow would we expect to see. Next good view of the poles came from ESA's Smart 1 mission. And here you see this ridge emanating from the bottom left of Shackleton. Earth is straight up in this picture, and the South Pole is roughly at the 10 o'clock position on Shackleton's rim. And these images are chosen because they show the sun coming from 2 diametrically opposite directions, and you can still see the top of the ridge. So this showed us that this ridge was a very promising site, potentially, for illumination for future landing operations. It also happened to include points A and B that we previously identified with Clementine. So we've had a wealth of missions recently, and the first significant improvement in understanding the conditions came from the Japanese Kaguya mission, and this had a laser altimeter that took the first laser altimetry data of the poles. And here we have another 2 more simulations. Again, the right-hand 2 are actually for the same lighting conditions, more or less the same lighting conditions as the previous simulations, one where the sun's coming from the near side and one from the far side. And the left-hand 2 are simulations using Kaguya topography. And you can see that they match really well. And in fact, we can determine that they match at the pixel level. But this was very exciting because this meant we could, for the first time, run simulations and have total faith in the results. So here we have something we did next, where we run simulations. This is a map. This is a movie for a whole year at 6-hour intervals. And so the sun's going around 12 times. And from the data that make up this movie, we are able to generate a bunch of useful parameters. This shows we can map out Earth and Sun shadows. So Earth shadows are here in blue and red, and Sun shadows are yellow and red. Of particular interest are regions in yellow. So these are permanently shadowed from the sun, so very cold, potential traps for volatiles, but they can at least see the Earth some of the time. So if you wanted to do a surface mission without a ComSat, you could at least you could get your data back if you time it correctly. So with as topography data from Kaguya and then from LRO has got better and better, we've been able to essentially fully characterize the illumination conditions. So what we do is we find which places have the most illumination, and then we do something as depicted here in the bottom right, where for a particular location, we fully map out its illumination history over the course of a year. And the Kaguya data were about 240 meters per pixel. The LODA data from LRO, they're now producing products about as up to, I think the latest is about 30 meters per pixel. So you're starting to get to the sort of spatial scale which is becoming very useful from a surface operations perspective. So we've gone all the way from a Clementine, which was at 500 meters per pixel, sort of go anti-clockwise. You end up now at the 30 meter scale. And the LROC camera, which actually has a high-res mode, the NAC camera, the narrow angle camera, takes data at about 50 centimeters. If you've not looked, they have some stunning imagery where they can actually determine some of the Apollo flags are still standing because they can see the shadow of the flag. But they do some interesting stereo data where you have the potential to have single-digit meter topography of certain regions. So as part of our LSI work, we developed a tool called Lunar Shader. And so we've been refining Lunar Shader for a number of years now, and it's very efficient and very precise. And so now that we have topography and image data, of very high quality, we're able to fully characterize the illumination conditions. And four of the key parameters, and these are of different values depending on the type of mission that you want to do. We found places near both poles which have constant sunlight for several months based around midsummer. What we put here is the maximum single period of illumination. Probably the best we found is about 8 months. So this means that if you want to have a surface, a lander, which can't survive any cold temperature, any eclipse periods, you could still have a useful mission that lasts for several months. Now we also determine all eclipse periods or shadowed periods. And potentially, from an engineering sense, the most useful is which places have the single shortest, longest period of shadow. And what I mean by that is, essentially, as you head to midwinter, which place is dark for the shortest period of time. And this is important if you want to have a lander mission which lasts for multiple years. Because in that case, if you want to last for multiple years, that you have to survive periods of darkness. It's very likely that you're going to need to use your batteries to heat your lander to keep it alive during those dark periods. And mass is all important. So you only want to take as many batteries as you need. And so you probably size your batteries based on finding the places which you have to heat for the least amount of time. Exact shadow locations become important as resolution gets higher and you want to plan rover traverses. If you want to do a long duration traverse, and it's very likely that if you can do some simulations to map out the exact location of shadows, that you can plan. One of the things we're working on is a rover traverse tool, which ideally keeps you in sunlight. You would enter where you want to start, where you want to finish, and the tool will work out, given the capabilities of your rover, can you actually get from A to B staying in sunlight, and how long would it take? Or if you do have to encounter darkness, how long do you have to encounter it for? And again, we can also investigate the effect of mask height. So again, images don't lie, so they tell you what the illumination is, but they only tell you for the absolute surface, and we want to be able to investigate if you put your solar rays on a 2 or 3 meter mast, does it make a difference? One of the other things we can now actually do with Lunar Shader is we can do communications analysis. So we can determine, well, Andy McGovern is my colleague at APL, who's the lead designer for the software. He's now got very nice variation of the tool for comms, where you can actually map out exactly which DSN station or a station that you're choosing can you see. One of the other discoveries we've managed to do now with the good global topography is, surprisingly, we found that permanent shadow can exist as far away from the poles as 58 degrees latitude, and this has implications for easier access to volatiles, potentially then to one of the going to a crater near the pole. So I'm going to leave you with this image. This was a high-definition TV. The Kagura mission had an HDTV camera on board, back when HDTV was very new. And these are available, actually, to look at on the web, and they're stunning. And this actually shows Earthset. The spacecraft would go. This is the South Pole. Shackleton is the crater just to the right of the A. And if you look carefully at the Earth, you'll see that you can see Australia just upside down, just on the left-hand side. And what's interesting here is I've marked the 4 places we initially found with the Clementine data have the most illumination. And you can see that they represent a relatively modest increase in topography compared to the surroundings. It's not like you suddenly have the Rockies or the Alps here. It's a very small hill, just in the right place. It can make a big difference to the illumination conditions that you experience. Thank you.